Hello, this is the topic 6 under the C3702 Introduction to Environmental Engineering. And this is fall one of the definition that we had, three definitions, right, in environmental engineering. Number one was to provide the ample, palatable, and safe drinking water. And the second one was the proper disposal of solid waste and the wastewater. Third one was the pollution control. It could be soil pollution, water pollution, air pollution, and noise pollution. So based on that, it looks like it falls under the definition number 3. So the our view, the learning objectives or competences at this modular topic align with one or more of the specific than the course objectives. The topic objectives are primarily aligned with the course learning objectives or outcome number 4 and 5. That means CLO 4 and 5. So these are basically identify common air pollutants and their pathways and determine the various technologies that are available for air pollution control. And number 5, CLO number 5 is interpret selected contemporary global environmental issues and emerging contaminants. So I arranged this one with the topic outline. The topic outline is the first one is the physical and chemical fundamentals, ideal gas law. Then it could be Dalton's law, partial pressure, adiabatic expansion and compression, and unit of measure. So the first three here are most likely, they are kind of review from the previous courses from physics, chemistry, and other courses. Units of measure is very important, so I'm going to discuss some of those over here. Then we'll do air pollution perspective, means what happens before, what happened, and why we are learning that. Air pollution standards, so meaning we'll do a little bit of air pollution standards in the sense of like say same as the water standards, right? So you know the water standards, so MCL, SMCL. Similarly, we'll have some kind of air pollution standards. Then effects of the air pollutants, we'll discuss three of those things: effects on materials, vegetation, and health. So these are the three things that we'll discuss. Then we'll discuss the origin and fate of air pollutants. So carbon monoxide, HAPs, lead, then nitrogen dioxide, photochemical oxidants, sulfur oxides, particulate matter. Then we'll see a little bit of micro and macro air pollution, indoor air pollution. Then we'll see contemporary issues. Out of the contemporary issues would be acid rain, ozone depletion, greenhouse effect, Lake Erie water pollution due to algae bloom, Flint, Michigan drinking water pollution due to lead. Then we'll see impacts of engineering solution in global, economic, environmental, and social context. Then we'll see a little bit of air pollution meteorology, like atmospheric engine, turbulence, stability, terrain effects. Turbulence and stability will give us a good weather, a bad weather, other cyclone or other things like that. Then we'll see atmospheric dispersion. We'll see a dispersion model as well. We'll see the different factors, what affects the dispersion model. Then indoor air quality model. I have this name over here, but we are not going to discuss a lot on that because time issues and other things like that. So air pollution control of stationary sources. That means the source that we know is stationary means from industry and other areas. We'll discuss the gaseous pollutants. There could be two types of pollutants. One is gaseous, other one is the particulate matter. So we'll see the gaseous pollutants, flue gas desulfurization is another option. Then the control technologies for nitrogen oxides, how we can control the nitrogen oxide. And last of all, we'll see particulate matter. So the learning outcomes or objectives for the student would be identify, interpret the criteria air pollutants. We'll discuss there are six criteria pollutants. 5 are the primary and 1 is the secondary. So describe the importance of air pollution standards and unit of measurements. Interpret the effects of air pollutants on the vegetation, materials, and health. Identify the origin and fate of air pollutants. Then explain the contemporary issues. Then we'll see discuss the air pollution meteorology, estimate the air pollutant concentrations in the downstream using dispersion model, then recognize the technologies and control devices used to control air pollutants. So we'll discuss at least 4 of them. So the physical and chemical fundamentals, ideal gas law, Dalton's law, partial pressure, adiabatic expansion and compression, units of measure. So this is the one we all know that from the previous classes. This is the ideal gas law. I'm not going to spend a lot of time on that because you guys have seen those in the physics, chemistry and other classes. So here is the PV, pressure and the volume is equal to nRT. So N, the number of moles per gas, R is the universal gas constant, T is the temperature in Kelvin. So Dalton's law, stack and exhaust sampling measurements are made with the instrument calibrated with the air. So Dalton found that the total pressure exerted by a mixture of gases is equal to the sum of the pressure that each type of gas would exert if it alone occupied the container. So in mathematical terms, total pressure PT is equal to P1 plus P2 plus P3 and so on. So where P total pressure and the other one. So Dalton's law also may be written in the terms of ideal gas law. That means pressure is equal to N RT over V, N2 RT over V, N3 RT over V, and equal to N1 plus L2 RT over V. So, N is the number of moles of different gases. Adiabatic expansion and compression. So an adiabatic process is one that takes place with no addition or removal of heat and with sufficient slowness so that the gas can be considered to be an equilibrium at all times. So this is adiabatic process, expansion, compression, process like that. So it's we saw those in previous classes, meaning physics, chemistry. So you guys should be okay on that. So units of measurement is very important for us to do here because of the air pollution. Unit of measurements, we have to have a two different one. Whereas in the water area, we know at least 5 or 6 different types, right? Like similarity, normality, milligram per liter, ppm, and percentage. At least 5 of those. So in the air, 3 basic units that we'll discuss here. Measurement is reporting the air pollution data, microgram per cubic meter, parts per million, and the micron, or preferably its equivalent, the micrometer, things like that. So anyway, converting microgram meter cube to ppm. So we will see like ppm is equal to mp. mp is the one that is given in microgram per meter cube. Then mw is the gram molecular weight, and 22.214 is the amount of the liter that is occupied by one mole of the gas, 1 gram mole of gas. T2 is the temperature, ambient temperature at which that we are taking the sample, and like this is the standard temperature, 0 degrees Celsius or 273 Kelvin. This is the ambient pressure and this is the standard pressure. And this is VA is the volume of the water sample, air sample we took, and 1000 is a conversion from meter cube to liter. So here is the ppm in water and ppm in air, right? So ppm in water could be volume in water mass to mass ratio, whereas in ppm in the air is volume to volume ratio. So that's the difference. This mass to mass is very unlikely for the air cases. Okay, so this is one of the example we'll see how to convert from a 1 cubic meter sample of air was found to contain 80 microgram of meter cube of sulfur dioxide, right? So in this case, the temperature and the pressure were 25 degrees Celsius and 103.193 kilopascal when the air sample was taken. What is the sulfur dioxide concentration in ppm? First, we'll do the gram molecular weight of sulfur dioxide. Sulfur is 32, oxygen is 16, then this is 2 is 64. Next, we must convert the temperature to absolute temperature. 25 degrees Celsius would be 298 Kelvin using equation 66 that we saw before. So ppm would be equal to 80 over this, then this is the one, and if I put everything together, I got 0.03 0 ppm of sulfur dioxide. So if it is 80 microgram per meter cube, then it will be 0.03 ppm of sulfur dioxide. So that would be the case in this case. So air pollution perspective. So basically air pollution is a public health concern on several scales: micro, meso, and macro. Micro is very small scale one, meso means medium, and macro is the bigger scale. Indoor air pollution results from products used in construction materials, adequacy of general ventilation, physical, chemical, geophysical factors that may result in exposure to naturally occurring radioactive materials. Industrial and mobile sources contribute to mesoscale air pollution, and the contaminants and the ambient air that surrounds us outdoors. Sorry. Macro scale impacts include transport of ambient air pollutants over large distances and global impact. Acid rain and ozone pollutions are the more examples of that. Global impacts of air pollution results from sources that may potentially change the upper atmosphere, for example, depletion of ozone layer and global warming. So we'll discuss that one a little bit more detail next time. In the following slides and other things. So then air pollution standards. 1970 Clean Air Act requires US EPA to investigate and describe the environmental effects of any air pollutant. So in this case, what the EPA used these studies to establish the National Ambient Air Quality Standard, NAAQS. The table 9.1 in the book, you can take a look. They have a different NAAQS standard in there, page 583. These standards are for all the ambient air, that is the outdoor air that normally surrounds us. EPA calls the pollutants carbon monoxide, nitrogen dioxide, sulfur dioxide, and PM10, and the particulate lead as a primary criteria pollutants, and the ozone the secondary criteria pollutants. And primary criteria pollutants is directly generated from the source as it is, and secondary one is the one they generated based on, like, say, multi combination of the two or other things together. So for example, ozone is like, say, most of the time ozone is created by nitrogen dioxide plus oxygen together, then it becomes the ozone O3 in this case. So the reason is that these pollutants were developed on health-based criteria. So mainly health-based criteria, that's why they call it primary criteria pollutants or secondary criteria pollutants. Ozone has effect, ozone has a good thing, I will discuss it more in there. The primary standards are established to protect human health with an adequate margin of safety. The secondary standards are intended to prevent environmental and the property damage, like ozone. Ozone have a little bit of health effect, but not a whole lot. In 1987, EPA revised the NAAQS. The standard hydrocarbon was dropped, and the standard for total suspended particulate (TSP) was replaced with particulate standard based on a mass of particular matter with an aerodynamic diameter of less than or equal to 10 micron, which is referred to as PM10 standards. So it could be PM 2.5 also, but PM10 is the main one that are used in this case. So states are divided into air quality region, AQR. So an AQR that has air quality equal to or better than the primary standard is called the attainment area. And those areas that do not meet the primary standard are called the non-attainment area. So the impact of the attainment area, non-attainment areas are if you want to build a industry that will have emission from there, then attainment area should be easy to do that. Non-attainment area could be hard because they will make more stringent rules for your emission and other things like that. So that's why they are divided into two different forms of things like that. So under 1970 CA Act, another established regulation for hazardous air pollution using a risk-based approach. These are called NESHAPs, National Emission, like standards for hazardous air pollutants. Because EPA had identified difficulty defining an ample margin of safety as required by the law, only 7 HAPs were regulated between 70 and 90s. So they are asbestos, arsenic, benzene, beryllium, mercury, vinyl chloride, and radionuclides. So total are 189 HAPs, but they did something like that. So we'll stop it here. So we keep it like so.